Have you ever stopped to think about steel? I mean, really think about it. It's everywhere, the backbone of our buildings, the frame of your car. We just sort of assume it's strong, right? That it does its job. But how do manufacturers know? Especially for the really critical stuff. Well, today we're doing a deep dive into exactly that, transforming steel quality control. We'll be looking at a really interesting breakthrough technology. It's called the Prometheus Segregation Analyzer, or ProSA for short. Our mission here is to unpack how this thing is basically changing the game for quality assurance in steelmaking. Moving away from, these old, slow methods, data something fast, data-driven, and that affects everything from the car you drive to the buildings we live and work in.
Yeah, and that's absolutely the core challenge steelmakers are grappling with. It's not just about meeting the minimum standard anymore. They have to consistently exceed really demanding expectations, especially for things like advanced high-strength steels, AHSS, and high-strength low-alloy steels, HSLA. With those materials, the internal quality, what's going on inside the slab, is absolutely critical to performance. And one defect that's been, well, really stubborn and costly is something called centerline segregation.
Okay, centerline segregation. Let's break that down. What exactly is it, and why is it such a pain for the industry?
Right. So picture a big slab of steel just after it's been cast while it's cooling down and becoming solid. Centerline segregation happens when certain elements they add to the steel alloys, like manganese, maybe chromium, don't spread out evenly. Instead, they kind of concentrate right down the middle, the center line of the slab. Think of it like a hidden flaw, almost an invisible weak seam running deep inside the steel. It can make that area weaker or more brittle, less consistent.
Okay, so it's an internal problem. How did they used to find this?
Well, that's the thing. The traditional ways are pretty brutal, actually. They're destructive. It means literally cutting a huge chunk out of this massive steel slab. Heavy work. Then they have to treat it with chemicals, etch it, basically, to make the internal structure visible. And then someone has to visually inspect it and grade how bad the segregation looks.
Wow.
Yeah. So the drawbacks are obvious, right? Slow, it's messy, potentially hazardous. It's also subjective, depends on the inspector's eye. And crucially, the feedback is way too late for immediate process improvements. You get the results maybe hours, even days later.
That sounds like a massive bottleneck. I mean, you could be making hundreds of tons of steel.
Exactly.
Before you even find out there was a problem in a batch made way earlier. That's got to be incredibly inefficient.
It is. A huge gamble, really. Wasted material, wasted energy, lost time, potential customer issues.
Yeah.
It all adds up.
So you need a way to see inside somehow without cutting it open, to catch these flaws before they become huge, expensive headaches. And that, I guess, is where ProSA comes in. This breakthrough tech developed by XRF Systems and ArcelorMittal Global R&D. It was shown off at AS Tech 2025.
That's the one. And what makes ProSA so different is how it sees inside. It's billed as the world's first industrial-scale XRF device for this.
XRF X-ray fluorescence.
Exactly. Think of it like a very sophisticated scanner. It uses X-rays, but instead of just taking a picture like in a medical X-ray, it analyzes the energy signature of the X-rays that bounce back off the steel. That signature tells you precisely which elements are present, manganese, chromium, etc., and importantly, how much is there, point by point, across the slab. It's like getting a chemical map of the slab's center line.
Then the big advantage.
It's completely non-destructive. No cutting, no etching, no visual guesswork. You scan the slab as is.
Okay, so no more destroying samples. That alone sounds huge.
Yeah, it is. It eliminates all that messy, time-consuming sample prep.
And you mentioned speed and precision. How fast are we talking?
We're talking rapid elemental mapping. For key elements like manganese or chromium, it can map a slab phase in under an hour.
Under an hour, compared to potentially days.
Exactly. And with really good accuracy, the error rate is typically less than 5%. That's a world away from visual grading.
And it's practical. I mean, steel yards are tough environments.
Oh yeah, it's designed for that. ProSA is mounted on a mobile, rugged cart. They can reel it right up to slabs stacked in the yard and scan them there.
So minimal disruption to workflow.
Right. And the output isn't just a good or bad rating. It's digital objective data, numbers. Things like the average concentration, the standard deviation, the width of the segregated zone. Perfect for feeding into statistical process control systems.
Replacing subjective judgment with hard data.
Precisely. And another practical point, it's designed to be safe. No need for the operators to wear personal radiation dosimeters, which simplifies things hugely in a plant setting. It's got safety interlocks, proximity sensors, built for industrial use.
Okay, so ProSA finds these segregation issues quickly, accurately, non-destructively, right in the yard. That's impressive. But the really exciting part, I guess, is closing the loop, right? How does getting this data faster actually change how they make steel? How does it prevent the problem in the first place?
That is the crucial step. Moving from just detection to actual control. Like we said, traditionally, maybe only a few slabs got that destructive test each day. By the time you found a problem, hundreds, maybe thousands of tons of steel might have already been cast with the same issue.
You're always looking backward.
Exactly.
Right.
Reactive, trying to fix problems after they've happened. With ProSA, they can scan dozens of slabs daily. And that data, those chemical maps, are available almost immediately to the metallurgist, the engineers running the caster.
So they see the problem much, much sooner.
Instantly, almost, which flips the whole thing on its head. You move from reactive correction to proactive prevention.
Okay, so what specifically can they do with that immediate data? Let's walk through the applications.
Sure. There are really 4 key ways this feedback gets used. First is caster parameter adjustment. The ProSA maps, especially for manganese, show exactly where segregation is worst across the slab width. If they see a pattern, maybe one area is consistently too rich in manganese, they can tweak the caster settings, things like the steel flow control or the secondary cooling strays right then and there, mid-shift.
So literally, an engineer sees the map on a screen, picks up the phone or sends a message, and tells the operators, adjust spray nozzle number 5.
Pretty much, yeah. Or adjust the mold oscillation or the casting speed. They have levers they can pull. And because the feedback is so fast, they can see the effect of that change on the next slabs coming off the line. It's a tight feedback loop.
Okay, that makes sense. What's number 2?
Second is slab sorting and downgrade avoidance. If a slab scan shows higher than normal segregation, even if they couldn't prevent it entirely, they can immediately flag that specific slab. Maybe it gets rerouted for a less demanding application where that segregation isn't critical.
So it doesn't automatically become scrap.
Right. Or at least it's diverted before it goes into a really high-spec product where it would definitely fail later on.
Yeah.
This avoids scrap, avoids customer complaints, saves money.
Smart. And number 3?
Third, it helps with caster maintenance scheduling. Sometimes the segregation patterns aren't just random. They show trends over time. Looking at the maps longitudinally, slab after slab, might reveal subtle signs of, say, wear inside the casting mold or a blockage starting to form in a nozzle.
So it's like predictive maintenance for the caster itself, catching equipment issues before they cause major quality problems.
Exactly. It gives them a heads up. Fix the mold or the nozzle before it starts producing obviously defective steel.
Okay, and the last one?
And finally, number 4, it's a massive enabler for statistical process control, or SPC, because ProSA gives you quantitative data, actual numbers like mean concentration, standard deviation, segregation width. You can track process performance statistically over time. Across different shifts, different crews, different casters, are things getting better? Are they drifting?
Right. For people maybe not familiar with SPC, it's basically using data to see if your process is stable and capable and spotting when things start to go off track.
That's a great way to put it. Before ProSA, the data for internal quality was sparse and subjective. Hard to do real SPC. Now you have this stream of objective quantitative data. It fits perfectly with modern quality management systems, things like Six Sigma or the IAPF standard for automotive suppliers. It drives continuous improvement.
So you're moving from like occasional snapshots to a continuous video feed of your internal quality. You can see the tiny wobbles before they become big crashes.
Precisely. It lets you intervene much earlier when the problem is small and easier to fix.
So ProSA really shifts from just being a diagnostic tool finding out what went wrong to being a preventative tool, helping stop problems before they even begin.
That's the core transformation, yes.
Okay, this all sounds great for the steel mill's more efficient, less waste, better process control. But let's bring it back to us, the end users. How does this better control over, manganese atoms bunching up inside a steel slab? How does that actually make a difference to the car I drive or the building I'm in right now?
It makes a huge difference, actually. It all translates to stronger, more reliable, more consistent steel in the products we rely on every day. Let's take a couple of examples. Think about automotive safety components. Your car's frame, the beams in the doors, the roof pillars, the parts designed to protect you in a crash. That centerline segregation can lead to something called martensitic banding, basically hard, brittle stripes within the steel. If those stripes are in a critical area...
They become weak points.
Exactly. Weak points that might compromise how the component performs in an impact. By using ProSA data to minimize that segregation variability, automakers get steel that behaves much more predictably. Components like door beams or roof rails are more consistently strong, making the car fundamentally safer for you.
So it's not just about meeting a spec, it's about reducing the hidden variations that could, in the worst case, affect crash performance. That actually allows for potentially lighter and safer designs too, right? If the material is more reliable.
Absolutely. When engineers have more confidence in the material's consistency, they can optimize designs further, push the boundaries safely.
Okay, what about bigger structures?
Well, take high-rise and bridge construction. We mentioned HSLA steel's high-strength low alloy. These are used for critical structural elements.
It's a kind of steel that needs to hold massive loads and resist the elements for decades.
Precisely. Things like bridge girders, columns, and skyscrapers. They need to withstand incredible stress, fatigue, corrosion, often for 50, 100 years or more. Uniformity here is paramount. Better control over internal quality, thanks to ProSA, means fewer potential issues at welds, which are often critical points. It leads to more predictable load-bearing performance over the entire life of the structure. Ultimately, safer infrastructure for all of us.
Makes sense. Anything else?
Even in things like consumer and industrial appliances. Maybe less dramatic, but still important. Think about the steel used for the casing of your washing machine, or maybe the racks inside a big data center server. These often need very tight tolerances, good surface finish, and good formability, the ability to be bent and shaped without cracking. Internal inconsistencies from segregation can cause problems during manufacturing, tearing, buckling, unpredictable springback. Using ProSA data to ensure more uniform steel helps alleviate these forming issues, reduces defects, and improves the speed and efficiency of production lines.
So, better quality control at the mill means fewer headaches and better products downstream, across a whole range of industries. And just to reiterate, this process system isn't just a concept in a lab somewhere, it's actually out there working.
Oh, absolutely. It's been successfully deployed and proven in the field. ArcelorMittal Dofasco, for example, uses it in their slab evaluation yard, and it's consistently delivering that full-width manganese mapping with accuracy better than 4% error. Plus, as we touched on, it has all those industrial strength features, safety certifications, integrated sensors, real-time controls, no need for dosimetry. It's built for the realities of a steel plant.
So wrapping this up, it sounds like ProSA has really changed the equation for steel quality. It's letting steelmakers move from reacting to problems
To proactively controlling the process, preventing defects before they happen.
It takes out the guesswork, closes that time lag between something happening and knowing about it.
Exactly. And it ensures that, slab after slab, the steel being produced is contributing to stronger, more uniform, and just fundamentally more reliable end products. The whole point is catching those potential defects early before they become really costly problems, or worse, safety risks.
So next time you're driving your car, or maybe just walking past a construction site with those huge steel beams, maybe take a second to think about the journey that steel took, and how an innovation like ProSA, working away quietly in a steel mill, is actually playing a role in ensuring the safety and reliability of so many things we depend on. It really is about solving problems right back at the source, isn't it? One carefully analyzed steel slab at a time.